I just wanted to take a quick second before I move on to the integrator to mention something practical about this circuit. If you were to ever try to build something like this, let me resize this and create some space for myself. If you ever try and build something like this in real life, what you notice that I did here is I basically have two op-amp circuits here, right? I've got on the one on the left, I've got an op-amp summing circuit, which gives us this output, right? V1 plus V2 plus V3 multiplied by a third, and it's going to be a negative output. Because the output's negative, I decided to implement an inverting amplifier, which gives us a gain of -1 to flip the output, so I could end up with a positive output voltage, right, to take the average of my three input signals. In real life, you know, if you were to build the circuit exactly how I had it in LT Spice, that would be perfectly fine. And depending on the resistor values and the capabilities of your op amp, this circuit could be perfectly fine in real life as well. However, sometimes in real life you do want to include, when I interface two stages like this, you do want to include a unity gain buffer in between the two stages. So let me go ahead and grab my thicker marker. It might be this one. Yeah. You might want to include a unity gain buffer here, where my input is this output of the previous stage, and then of course I tie my negative terminal back to the output, and that's my unity gain buffer. And so what I'm going to get here, of course, is that the output voltage V out is going to show up at the plus terminal. Because of the op amp rules, it's also going to show up at the minus terminal, which is my output, right? And so I'm still going to get this V out to be the input to the inverting amplifier, which is exactly what I wanted. The difference now is that I won't pull any extra current from the output. And if your op amp's strong enough and it can provide enough current, it could be perfectly fine without this stage. But if it's not, then this circuit that you attach here could pull a substantial amount of current from your op amp and could affect the performance of your first stage here, your summing circuit. And so it could be smart to include an op amp, basically a voltage follower or a unity gain buffer here, because we know that there can be no current flowing into the input terminals of such an op amp. That's one of the golden rules, right? So I would ensure that no current flows this way, and I would maintain the operation of this circuit, and then this circuit still sees the exact same input, right? This V out that was originally being fed directly in is now just being fed in through a voltage follower, and everything will work exactly the same, okay? So I just wanted to throw that out there as a practical note, because this is practical when you interface op amps, cascading. That's what this is called, cascading op amp circuits. Basically, I have cascading is when I feed the output of one into the input of the next one. When I cascade op amp circuits, I typically want to include a voltage follower in between stages. It's not 100% necessary, but you can't go wrong if you do include one, okay? So if you have, you know, an extra op amp on the chip that you're using or whatever, you could always implement this to just guarantee that you won't cause any issues by interfacing the two circuits. Okay, so I'm going to go ahead and end this video. I know that that's maybe even a little too practical for this class. There's no lab component. This isn't going to matter, but I do like to throw practical notes in there. So if you have any questions about this, feel free to ask. But I'm going to go ahead and end this video right here, and we'll move on to the integrator, the op amp integrator.